Hi everybody, and thanks for taking the time to join me in exploring the basics of one of our accredited parameters at Intercal. Light meters, or more correctly illuminance meters, are used to measure the intensity of light falling on a surface. Amongst other things, they are used in workplaces to ensure that the eyesight of workers is not compromised and thereby meeting health and safety requirements. Accurate readings, of course, therefore, are of paramount importance. I have entitled this presentation Photometry, from first principles to final practice. And I will cover first the basic principles of photometry, and then I will go on to show the implementation of these principles in the construction of various photometry laboratories, including the laboratory at Intercal. The electromagnetic spectrum is very wide, from low frequency radio waves to high frequency gamma rays, and we use different regions of the spectrum in various parts of our daily lives. Radio waves are used to transmit radio and television signals. Microwaves are used for cooking, radar, mobile phones, Wi-Fi networks. When we need to heat a room, the heat energy is in the infrared band, while frequencies in the upper regions are used for medical purposes. Probably the region that we use the most in our everyday lives, though, is the region of visible light. Visible light for humans is bounded by red light on the lower frequencies and blue light on the upper frequencies. Some animals are able to see into the infrared region and some insects into the ultraviolet region, but we are concerned only with human eyes in photometry. The visible light band is the region of the spectrum to which our eyes are sensitive, and they produce signals that our brains interpret into images. In metrology, the measurement of the electromagnetic spectrum as a whole, including the visible light region, is referred to as radiometry. However, the measurement of light levels in the visible region is called photometry. Why do you think there is a difference? When the whole spectrum of visible light is available to our eyes, we see it as white light. But when the white light is separated into smaller frequency bands, our eyes interpret these as colors. This separation may be directly through a prism or indirectly by the color of the surface. Here you can see that most of the frequencies or colors in the white light are absorbed by the leaf, but the green light is reflected, so we see the leaf as being green. The problem, though, is that our eyes are more sensitive to particular colors or ranges in the visible light spectrum. The solid line on this graph shows the typical response of the eye in bright light, what we call the photopic response. Here you can see that the eye is more sensitive to colors in the green-yellow region and less sensitive to colors in the blue and red regions. This is why green and yellow colors look brighter than red colors. In this example, a green tile and a red tile are both exposed to the same light source, but with everything else being equal, the green tile will look brighter. When you have your eyes tested by an optometrist, they will often show you a slide such as this and will ask you which is brighter. The optometrist does this to check the color sensitivity of your eyes. Going back to this graph, the dotted line is the sensitivity of the eye in dim light conditions, what we call the scotopic response. The parts of the eyes that work best in dim light are more sensitive to the blue region, which is why we tend to see less colors at night. In order to measure ambient light conditions, then, we use illuminance meters, also known as lux meters or light meters. These meters do not just measure the level of light energy that is falling on the sensor. The measurement is biased in such a way as to compensate for the eye's sensitivity to different colors. So they measure the apparent illuminance based on the color sensitivity of the human eye. Now, I've been using the term illuminance, but let's make that term clearer by taking a quick look at other terms used in photometry. A uniform light source radiates energy in all directions. This is known as luminous flux and is measured in lumens. Luminous flux answers the question, what is the total energy being emitted by the light source? An observer on one side of the light source would see a bright light. This is luminous intensity and is the amount of light emitted in one direction, measured in candela. Now the candela is one of the base SI units, and the word candela is Latin for candle, because a typical wax candle will have an intensity of around 1 candela. Luminous intensity answers the question, how bright is the light as seen by an observer? That same light emitted in one direction falls onto a surface. Illuminance is the measure of how much light falls on a surface in a specified area. This is what illuminance or light meters measure. The unit of illuminance is lux, which is why illuminance meters are often called lux meters. Illuminance is the measurement of how much light reaches the surface. Finally, that same light is reflected off of the surface. Luminance tells us how bright the surface appears, and the unit is the nit. With the same light source, a white surface would appear brighter than a darker surface because more light is being reflected off of the white surface. Luminance answers the question, how bright is the surface? Note that luminance should not be confused with illuminance. In summary then, we have luminous flux, telling us how much energy there is in total in all directions. We have luminous intensity, telling us how much light is in one direction or how bright the light source appears. Illuminance is a measure of how much light falls on a surface, and luminance is the measure of how bright the surface appears. In the calibration of illuminance meters or light meters, we concern ourselves with luminous intensity, or how bright is our reference lamp, and illuminance, or how much light is falling on the illuminance meter being calibrated. So back to the question of why do we need to calibrate illuminance meters? One of the main uses of illuminance meters is for health and safety reasons. Labour and building regulations dictate that different occupations and different areas in buildings have minimum light levels based on the work being done and the need to be able to see clearly. Obviously, stairwells need to be lit so that people don't fall down the stairs, but the light level does not have to be as bright as someone performing fine work. For example, regulations say that in assembly areas, workers that are performing fine work, such as repairing radio equipment, there should be an illuminance of at least 500 lux. For even finer work, the light level on the work surface should be at least 1000 lux. Entrance halls and reception areas can be dimly lit, but at no less than 100 lux, while your general office and conference rooms must be lit to at least 300 lux. Computer and business machine operators must have at least 500 lux on their work surfaces. In areas that affect us in the calibration and test community, our laboratories must have minimum lighting levels of 200 to 300 lux. Failure to meet these light levels would put strain on the eyes of the workers, resulting in long-term health and sight problems. By the way, the minimum level of 300 lux is a lot brighter than you would think. It is a good idea to have a light survey regularly performed on your work areas. So how should light levels be measured? Firstly, place the light meter sensor on the work surface. This is where the worker's eyes are focused, so this is where the minimum light levels must be maintained. Walking around with a meter in your hand would mean that the meter is closer to the light fitting and will read higher than if it was on the work surface. So measure the illuminance at the workplace of each worker. Then close the blinds or curtains. There may be plenty of natural light during a sunny day, but overcast conditions or late afternoon will have much lower natural light levels. Light falling on a work surface must be measured in the worst conditions, so natural light should be eliminated by closing the blinds. Then leave the light meter on the bench and move away. Your body may cause shadows, or light-colored clothing may reflect ambient light. So now that we know why rims calibrate, how do we go about it? As I mentioned before, we use a standard light source. This source is usually a tungsten lamp, although LED sources are being used more and more. The lamp is calibrated for a known luminous intensity measured in candela. In this diagram, the lamp has a luminous intensity of 1000 candela. It is worth noting that this calibrated luminous intensity is usually measured in one direction only for lamps used to calibrate illuminance meters. Obviously, the lamp needs power, and these are often specialized units. A 1000 candela tungsten lamp draws around 600 watts, and it must be very stable in order to keep the intensity steady. The calibration certificate for the lamp gives the luminous intensity for a certain applied voltage and measured current. Only when these are correctly applied will the luminous intensity be the same as the calibrated value. We'll talk more on applying power to a lamp a little later. Remember that the lamp is calibrated in candela, but we are measuring lux. It can be seen that the closer the measurement is made to the lamp, the higher the reading on the meter, even though the lamp remains the same. In this diagram, we can see this represented by the three arrows emanating from the lamp. All three are hitting the meter sensor. If we move the meter further away, then the illuminance is reduced, and we get a lower lux reading on the meter. In the diagram, only one of the arrows is now directly hitting the sensor. In fact, illuminance in lux is proportional to the inverse square of the distance from the light source. Obviously then, in order to determine the illuminance value in lux, at the sensor we need to know the exact distance between the light source and the face of the meter. Since the luminous intensity of the lamp remains constant, in order to obtain various illuminance values, we have to move the meter closer to and further from the lamp. Remembering that the calibrated luminous intensity is measured in one direction only, the face of the meter must remain in the light path regardless of its distance from the lamp. There must be mechanisms in place to perfectly align the meter with the lamp at any point on the light path. Speaking of alignment, the face of the light meter must also be aligned to the lamp, both vertically and horizontally. Any misalignment will cause errors proportional to the cosine law. The laboratory must therefore have methods in place to perfectly align the meter to the lamp before calibration begins and to keep it aligned during the calibration process. To calibrate a meter, we need to determine the illuminance on the face of the meter. As we have seen, this is determined from the calibrated luminous intensity of the reference lamp along the light path. The problem is that the lamp emits light in all directions, and some of that light is reflected by the surroundings towards the face of the meter. To reduce the reflections, we create a tunnel around the light path using baffle plates. These are inserted between the lamp and the meter, and the reflected light reaching the face of the meter is greatly reduced. So those are the basic principles of photometry. Let us see how the theory has been put into practice. This is a typical commercially available photometry bench. The frame is solid steel for stability and trueness. The lamp is fixed at the far end, and the meter being calibrated is mounted on a trolley that runs on tubular rails. You can also see a baffle plate mounted between the lamp and the meter. Also notice that the wall and ceiling of the room are dark. This helps to reduce reflected light. This bench is about 4 meters long, and depending on the intensity of the lamp, can be used up to around 4000 lux. NMISA has a bench similar to this, and theirs is fitted with linear transducers to give the distance between the lamp and the meter to within a few fractions of a millimeter. At the other end of the complexity scale, this is the photometry system at the PTB in Germany. This one is 40 meters long. Yeah, you heard that correctly, 40 meters long. It can be used as one continuous bench when you need the meter to be very far from the lamp, or it can be sectioned into 3 separate benches, each with its own lamp and control system. This particular bench is good for up to about 10,000 lux. This is or was the photometry system at the NIST, the NIST laboratory in the USA. Here the various important parts are labelled. You can see the rails and the carriages on which the lamps and the meter are mounted. What is interesting here is that several meters to be calibrated are mounted on a carousel. This means that each meter can be calibrated in turn without disturbing the setup. Notice that the system is enclosed in a tunnel-like box. Sections of the sides can be removed to give access to the lamp and to position the meter. However, this is the old NIST photometry bench. that was only capable of achieving uncertainties of measurement for illuminous responsivity at around 0.5%. This is the new bench at NIST that was completed in 2019. It is a lot more complicated, more expensive, but has more features and is more accurate with uncertainties in the order of 0.2%. Multiple meters can be installed on the UET rack and each can be remotely moved into position, similar to the carousel in the old system. And this is the photometry bench at Intercal. The lamp is mounted on the left in this image and the meter being tested is on the right. Baffle plates have been installed between them. The lamp has been lit with reduced power to protect our camera, but you can easily see the light path controlled by the baffles. In this image, the laboratory lights have been switched off. The effect of the baffles is now more noticeable as the area beyond the baffles is extremely dark. Another illustration of the effectiveness of the baffle plates can be seen in this image. This is the meter's view of the lamp when no baffles are in place. You can see that the light is reflected off of the wall and the curtains and the rails. The bottom image is the same view but with the baffles in place. Now only the light from the lamp reaches the meter. As mentioned earlier, the lamp requires a high power and very stable power supply. The lamps have tungsten filaments and must be treated with extreme care. This applies not only to the handling and storage, but also to the way the power is applied. If the full power is simply switched on and off, the filament will receive a thermal shock and will rapidly deteriorate. This not only reduces the lifespan of the very expensive lamp, but it may also affect the calibration values. Consequently, it is good practice to slowly and smoothly increase the power to the lamp over several minutes to get it to full intensity, and then also slowly reduce the power when the calibration is complete. We found that trying to do this manually was not only slow and time-consuming, it also required infinite patience and was often rushed. This was to the probable detriment of the lamp. So to remove the human factor from damaging the lamp, a custom power supply controller was built. This controls the power to slowly ramp the power up in order to allow the lamp to thermally stabilize. At the end of the calibration, the power is also reduced in a controlled manner to allow the lamp to cool properly. The system also logs the amount of time that each lamp has been lit, and this helps us to determine the recalibration interval for each lamp. Finally, as boring as they are, we must quickly touch on the major contributors to the uncertainty budget. The largest contributor to the uncertainty budget is the calibration of the lamp. At this time, NMISA is able to provide calibrations of the lamps with uncertainties of around 2.5%. For smaller uncertainties, other NMIs in the world can provide calibration uncertainties of less than 1%. As mentioned earlier, the luminous intensity of the calibrated lamp is measured with a specific current and voltage being applied to a power supply. This power supply must be repeatable and stable to within a few milliamps and millivolts in order to prevent significant uncertainty contributions. Another major contributor is the distance of the meter from the lamp. Since illuminance is inversely proportional to the square of the distance, the closer the lamp is to the meter, the higher the uncertainty contribution by the distance measurement. For example, a 2 mm error at a distance of 2.5 meters will give an error of around 0.2 lux. But the same 2 mm error at a distance of 0.5 meters will give an error of around 24 lux. Finally, the face of the illuminance meter must be perfectly aligned with the calibrated face of the lamp, both horizontally and vertically. Since any misalignment will affect the value indicated by the meter, the uncertainty of the accuracy of the alignment in both directions is a contributor to the uncertainty budget. So there we have it. I've explained what photometry is and how it differs from radiometry. I then went through the basic principles of photometry, explaining luminous flux, luminous intensity, illuminance, and luminance. We saw where illuminance meters are used and how to use them. I then explained the calibration principles of illuminance meters and the contributors to the uncertainties. We then took a quick look at the designs of photometry benches around the world and also how we implemented all of this into the photometry laboratory at Intercal. Thank you all for your time and your interest.